Good morning. We covered page 2 and a little bit of page 3 already, so I'm going to pick up with units, basic units of measurement. For mass, we will talk about grams or kilograms. Volume does not have a standard amount because it changes very quickly. So one of the important relationships we need to know is the relationship between using milliliters in a piece of glassware measuring volume in the lab to volume by measurement, where we would measure, for example, 3 edges of a cube to get 1 centimeter cubed. So this is one of our definitions. Remember, the 3 lines means that it's an exact definition. 1 milliliter is 1 cubic centimeter. In the health sciences, we sometimes hear this referred to as 1 cc, cubic centimeter. Now, volume is interesting because it changes very rapidly. So, for example, if I tripled the edge measurement of that cube in all of those directions, then the volume would increase significantly. And we can't see the back edge of that cube. So when we calculate that volume, we would take 3 centimeters and we would cube that whole thing. Now when we do that, we need to distribute our exponent to the number and also to the units. So that is going to give us 3 cubed centimeters cubed, and that equals 27 centimeter cubed, or using that relationship, 27 milliliters. So if we triple the distance of that edge length, we actually get 27 times the volume. It changes very quickly. And so for that reason, there's no standard given in the SI unit system. It just changes very rapidly. Now we have some of these English systems. These are all definitions: gallons to quarts, quarts to pints, and pints to cups. You do not need to know these. I will always give them to you if you need them. But you will see them in the grocery store. All right, we talked a little bit about temperature in terms of heat energy. And we will look at some calculations with those a little later. Scientific notation as well. I believe we covered this in another video, but this was clearly a format. So make sure that you just have 1 digit in front of the decimal place. If you have something like 23.6 times 10 to the 2, that is not scientific notation. That's an engineering format. The number can be correct, but it's not the format that we call scientific notation. So be very aware of that. I believe I did complete these in another video, so I wanted to skip ahead. Here's our SI units. Notice in the metric system, here we have the metric system over here, and here we have the SI system, and we have meters, our standard for kilograms, seconds, and Kelvin for units, but there's no volume in that SI system. We also covered the metric prefixes and some of these conversions, these equivalent statements, which we can write as unit factors. And let's see, we got all the way through these significant figures. I'm going to ask you to bring a calculator to do this exercise together as a breakout group. So we will do that, and I'll give you another one. I'm going to ask you to also divide this. So let me just add that. 3.75 times 10 to the 15th, and then we're going to divide that by 8.605 times 10 to the 4. All right, we'll discuss unit factors. And I did mention these. Here are the instructions for dimensional analysis. So I'll be referring back to those. But first I'm going to jump ahead to using our metric prefixes to do these conversions. So we said earlier that 1 kilometer, that's a K, and the K means what? Where that K is, I could just substitute the value. So let's just remind ourselves what those values are. So at our 1, our middle, as we go up, we go 10 to the 3rd, 10 to the 6th, 10 to the 9th, and there's our K, kilo. Kilo means 1,000. So I can write this two ways. If I have 1 kilometer, that must be 1,000 meters. Or, depending on what I need in my calculation, I could also say there are 1,000 meters in, means divide, 1 kilometer. Let's take a look at this one. Here we have the M. Let me complete my chart. We have, in this region, we have 10 to the minus 1, 10 to the minus 2, and then we get to 10 to the minus 3, and that's my milli. 10 to the minus 6 is micro, and 10 to the minus 9 is nano. So that milli means 10 to the minus 3. That's already in there. So what value do we put to make it true the way it's written? Well, if this is, we're saying how many milligrams, which one's bigger, which one's smaller? This one is the larger size, larger, and this is the smaller side, so we're going to need a lot of those. What number will make that equal to 1? 1,000. So this is not the same direct substitution we saw with kilometers. Instead, we're using 1,000 small milligrams to make 1 gram. So essentially these values cancel each other out to make 1 gram. So let's write that as a factor. 1 gram must have 1,000 milligrams, or depending on what my question needs me to do based on the units, I could say there are 1,000 milligrams in 1 gram. Now if you wrote this slightly differently with a different number, that is also fine. For example, if you're making your factor here just out of the blue, you could just fill in, let's say there's grams and milligrams here. You could say, well, 1 milligram is 10 to the minus 3rd grams. So if that's what you wrote, that's totally valid. If that's confusing, pick one way to do these conversions and stick with it. Find the way that works for you and use it each time. So I'm going to come down to this section. I'm going to use dimensional analysis. So I'm going to start with what I'm given. I'm going to use dimensional analysis. So I'm going to go back to that first step, write the units of the answer. I like to use a question mark. This helps me know where I'm going. So I'm looking for seconds. How many seconds? Now, the official abbreviation is just an S, but because of the way it looks when we write it, it looks like a 5. It's a little bit unclear. In my own personal work, I write out SEC so that I see that it's seconds. And then I'm going to write what I'm given. So this is step 2. Determine what information to start with. So that's usually given in the problem. So 175 milliseconds, and I need to do something that converts that into seconds. I need to go find that relationship. Now I'm going to use the units to line it up correctly. Here are examples of my unit factors. So I'm going to write, I'm going to write milliseconds in the denominator because those don't appear in the answer I'm looking for. What does appear is seconds, so I'm going to write that on top. And I can see from the units that these will cancel, and when I fill in the numbers correctly, that will give me the correct answer. So, how do we want to do this? Well, we could say 1 second contains 1,000 milliseconds. And so that answer, I would just take 175 divided by 1,000 is 0.175 seconds. So let's do that same thing for these next two. We're looking for milligrams, and we're starting with kilograms. So now what I've done is rewrite the question in math. Following dimensional analysis, I see that I need to cancel out those kilograms. Let me write that a little bit more neatly. I'm going to put kilograms in the denominator on the bottom. And, oh, I can't go directly to grams. I recommend when we look at that chart right here, when we use this chart right here, always go through unity. So don't try to go from milli to kilo or something like that. You can do it, but it can introduce sources of error, and you don't need any extra sources of error. So let's just go from kilograms to grams. Then we won't have what we're looking for. We need to cancel out the grams, and then we'll go from grams to milligrams. So we have set up a series of relationships that are true. We can fill in numbers that are true. And we'll use the units to line them up so that at the end, I just have milligrams equals milligrams. And that's a good indication that my calculation will be correct. So we just need to fill in these numbers correctly. Let's see. 1 kilogram has 1,000 grams. 1 gram has 1,000 milligrams, just like we had up here. So I'll put that into my calculator, and I will keep that 0 because it's shown here. It would not be shown there if it wasn't significant. So that gives me, 1.20 times 10, and it's just a big number. I need to show the significant figures, so I'm going to go ahead and put it into scientific notation. Times 10 to the 5 milligrams. Now in this third example, we have units in the numerator and the denominator that both get converted. So I'm going to look for kilometers per hour. How many kilometers per hour? And I'm going to start with this value. And again, let's write that slanty line. Let's write that with a clear numerator and a clear denominator. So that is 3.00 times 10 to the 8th meters on top, and that is per 1 second on the bottom. So again, I've just written the question in terms of math. Now you can see what to do using the units. I need to cancel out meters because they don't appear in the answer. And what does appear is kilometers. So now I go find the numbers that make that true. Let's see, 1 kilometer is 1,000 meters. And now I've gotten rid of my meters, so the numerator is done. Next up, we have hours in the denominator, so we need to get those in there somehow from seconds. We don't have seconds over there, so I'm going to multiply seconds on the top so that they cancel, and come up with relationships that will get me closer to hours. Now I like to go through minutes because I know 1 minute has 60 seconds. And I like to make that a separate step because it's easy to write 1 second has 60 minutes, and that would be wrong. So take a moment as you write those numbers in to make sure that you have written them correctly. You haven't flipped the values. So we'll use the units to determine how the relationship should go, and then be careful to fill in the numbers to make it reflect what you wanted. All right, we've got to cancel out minutes because they don't appear over here. And we're going to go to hours. So what numbers make that true? I'll go ahead and show my units canceling here. I'm left with kilometers on top, hours on the bottom. And then I'm going to put that into my calculator. The way I like to do this in the calculator is to just go in order. So I will do 3.00 times 10 to the 8th using the exponent button. And I'm going to divide by 1,000. And then I'm going to multiply by 60 and multiply by 60, and then I hit the equals button. We've got a bunch of zeros there, so I'm going to put it into scientific notation, and I'm going to count the zeros. I have 3, 6, 9 times 10 to the 9. Is that correct? Yep, divide 1,000 times 60, 3, 6, 7, 8, 9. And those units are going to be kilometers on top and hours on the bottom. Okay, we skipped a couple harder problems. Oh, we have one more here. Oh yeah, we'll keep going with this. All right. For this one, we need to go from centimeters into kilometers. So how many kilometers equals 3.50 times 10 to the 7 centimeters? So go ahead, stop the video, complete your calculations, and then click play again. I'll cancel out centimeters because they don't appear on the other side, and to get closer to kilometers, I'll put meters in the top. Then I'm going to divide out those meters so they cancel and convert to kilometers. So this is my solution path based on the units, and now I'll fill in the numbers. 1 meter has 100 centimeters, and 1 kilometer has 1,000 meters. And now I'm just going to do the math for that. I have 3.5 times 10 to the 7 divide by 100, divide again by 1,000, and I get 350. Are we done? No, we need that decimal place because that 0 is measured. And our units are kilometers. So let me just make note of that. This is a measured 0. So it is significant. All right, next up we will do some metric English conversions. And again, we have these units, pounds. I like to write pounds in cursive. I feel like I've already done this in a video. Okay, so how many kilograms equals 155 pounds? And I'm going to write that in cursive just so that it doesn't look like a number, like 1, let's see, 1BS can sometimes look like 165. So I just write it in cursive. Now we need to go find a relationship. We need to cancel out pounds and go to something that brings us closer. And we gave these, oh, I think they were, there's a little table. Here they are. I'm going to use this one. That will get me closer. 1 pound is 453.6 grams. So 1 pound is 453.6 grams. Great. Pounds are out of there. Now, let's cancel out grams. Oh, and we just go to kilograms. So we'll end up with kilograms equals kilograms. We'll take 155 times 453.6 divided by 1,000. And we get 70, excuse me, 0.308 kilograms. I lost my line there. And that has 3 significant figures, so I will underline the 3, and if I'm going to round that, that will be 70.3 kilograms. All right, we'll do a couple more. How many cups can, in a 2.0 liter bottle? We'll need to cancel out liters. And here we have these pints and cups, but how do we go from cups to liters or liters to cups? Well, let's go look at that table again. There it is. Quarts. Quarts to milliliters, 946. 1 quart is 946 milliliters. All right, this needs to be milliliters. 946 milliliters is 1 quart. All right, we've got a couple conversions left to do, so take a moment and get that started. And we'll go from quart to pints because that's what we have here. And then we have to cancel out pints and go to cups. So now I'll fill in those numbers. Let's see, 1 quart is 2 pints and 1 pint is 2 cups. So our value will be 2 divided by 946 times 2 times 2. That can't be right. I have one more conversion to do. And that is here. I didn't cancel my units. Quarts, pints. But here I've got that milliliters, liters mismatch. And my answer kind of told me that. So let's see, I need to get rid of milliliters on top and cancel those with liters on the bottom. Here we go. Now I can cancel that with that and that with that. It's all multiplication and division, so the order of the factors doesn't matter. You can write them in any order. And so my answer is 8.456. And that is only good to how many sig figs? 2. So when we round that, that will become 8.5 cups for my rounded answer. In the next one, we have 2 factors again. Calculate the speed of light in meters per second. So how many meters can it travel in 1 second? And we're going to start with a light year. This is a distance in 1 year. In means 1 over. So let's start by writing a factor of that given information. So let's put our distance on the top. and we have 5.88 times 10 to the 12 miles. That is MI, that abbreviation. And that is how far it can travel in 1 year. So again, we have two conversions to do. One on the numerator and one on the bottom. And each one may be a series of relationships. So let's get rid of miles down here. And we need to go to something that's closer to meters. So let's see what we've got in our table. Well, inches doesn't really help us. But I think we have it in our conversion factors. Where else did we? Oh, yes. Here we go. Look at that one. Kilometers to miles. Ah, and there it is again. I like that one better because it's got 4 sig figs. So let's see, how many do we have in this problem? We have 3. So we want to go to kilometers, and it is 1.609 kilometers per mile. Let me just double check that. Oh, it's given right here. There we go. Great, so miles are out of there. And we have to get rid of kilometers and go to meters. And we know that 1 kilometer is 1,000 meters, which means the numerator is done now. All right, now we have to go from years into seconds. So years. I am going to go to days. Then I'm going to go to days to hours, and hours to minutes, and minutes to seconds. Now, if you remember about leap years, we actually have 365.25 days in a year, but that probably won't make a huge difference in your answer. 1 day has 24 hours. 1 hour has 60 minutes, and 1 minute has 60 seconds. So plugging that in, I have 5.88 E12 times 1.609 times 1,000, divide by 365.25, divide by 24, divide by 60, divide by 60, and I get 2.997 3 sig figs times 10 to the 3678 meters per second. If I'm going to round that, these all flip up and we get that number we may have seen before, 3.00 times 10 to the 8th meters per second. Let's take a look at our temperature conversions. Now, one reason I like to do this after we've talked about significant figures is because we have a mixed calculation. So when we look at these, this 1.8, this is an exact conversion. We've defined the size of the degrees in that energy scale and the shift as well. But we do have addition subtraction, and so we have to look at decimal places in some of our calculations. So specifically, the Kelvin to Celsius conversions are very important, and that has that decimal place consideration. So let's take a look at this one. We're going to go from Kelvin. First, let's go to Celsius. So how many degrees Celsius is 77 Kelvin? Using this equation, we'll subtract off 273. And does that make sense? Are we allowed to have negative temperatures there? Yes, we are. So that's pretty cold. Liquid nitrogen. It's pretty cold. All right, now we're going to go to Fahrenheit. So how many degrees Fahrenheit equals 196 degrees C? Well, let me look up at those formulas here. And I'm going to use this one. So I'll multiply by 1.8 and add 32. So I get minus 384.8 degrees F. And again, we have values that go just to the ones place. So our rounded value would go to negative 385, very negative temperature. Okay, and that brings us to measuring volume. A little bit of practice with some volume calculations. So we could measure the volume of a liquid directly using, I am going to go back and work on these calculations up here. I left some of the hard ones at the very beginning. Okay, so for these problems, we're going to use dimensional analysis. We will look at the units that we're looking for and the units we're given and determine a series of relationships that turn one into the other. So we're looking for how many yards. How many is a question mark? And we're looking for yards. That's a distant measurement. And we're starting with 26.2 miles, which is the length of a marathon. 26.2 miles. Well, here we have conversions given in the problem from miles to feet and feet to yards. So let's just line those up. Miles will go in the denominator, and we'll take that to feet. Fill in the numbers. And we're going to cancel out feet and go to yards. And that is exact, these are both definitions. 1 yard is 3 feet. Make sure that you fill in the numbers corresponding to where you put the units. So 26.2 times 5280 divide by 3, and I get 46112 yards. Now to identify our significant figures, we look at our initial problem here. It had 3 significant figures. So I'm going to underline the third number from the left. And then that rounded value would be 46100 yards. Okay, let's do another one. In this problem, we're looking for how many hours. How many hours does it take to get to Madras, Oregon from Seattle? We have a distance and we have this rate. So that we can write separately as a factor. So let me just change colors here, and we can make that into a clear numerator and a clear denominator. That is 65 kilometers per 1 hour. And we can flip that however we want. How might we want to flip that in this problem? Well, I see I'm looking for hours, and that has hours in the denominator. So probably that's going to come into our calculation flipped upside down from the way I wrote it there. Now I'm going to go ahead and start with 285 miles. That is often what students pick to start with. So how many hours does it take to go 285 miles? Well, I see up here I've got kilometers. So let's go ahead and do that conversion we saw. Miles to kilometers. Here it is. 1 mile, 1.609 kilometers. Great, miles are out of there, so we're making progress. Now I see that factor has kilometers in it, and that is going to take us into that time unit. Oh, then I think that's it. In 1 hour, we can go 65 kilometers. Get rid of that unit, and we have hours equals hours. So 285 times 1.609 divide 65, and I get, oh, let me make that the same color. 7.054 hours. What is our limiting number of significant figures? Well, let's see, we have 3 in this. This one we have 4. That is a measured conversion. And we usually want our data to limit the significant figures. We wouldn't want to use a known conversion rounded to fewer significant figures than our original data. This is another piece of our data. This has 2 significant figures. So our answer will have just 2 significant figures. When we round that, it's about 7.0 hours of driving time. All right, one more example using dimensional analysis, and this has a numerator and a denominator. We're looking for miles per hour. How many miles per hour is the speed of light? So remember that per means 1 over. So we'll write 2.998 times 10 to the 8th meters. You see we have a distance on top. We're going to convert it to miles, which is another distance, per 1 second. So if it just says per second, that means that's the speed for 1 second. Okay, so let's see, meters will cancel there, but here I have kilometers up here. So let's convert this into, let's convert this into kilometers here to start with. And then we can cancel out kilometers and go to miles. Okay, so now we can use that relationship in example 2. Now next up, this is another place that time conversions are a little more familiar, so it's easy to make mistakes with those. We want to end up with hours, but we're given seconds. So to get rid of seconds, I'm going to multiply by seconds on the top. And then to get to hours, I like to go through minutes, minutes to hours, and then we'll be done. So 60 seconds in 1 minute, 60 minutes in 1 hour, and let's take a look at our units. Gone, gone. Miles equals miles, good. Minutes, seconds cancels out over here, and we end up with miles per hour. Okay, so let's put in the values. There is my answer in the calculator. So we have to do a couple things with that. First, we have to look at the significant figures. How many significant figures? Let's underline the last one. I'm going to underline that 7 right there. Those time conversions are exact. And the kilometers to meters conversion is exact. The miles to kilometers conversion has 4 significant figures, it's measured. And our original data, that speed of light, has 4 significant figures. So I'm going to rewrite this in scientific notation. So that's 6.708. That 7's going to flip my 7 up to an 8. And then I'm going to write a factor that makes the value the same. And that is miles per hour. Okay, so that's our rounded answer. All right, the last section of this worksheet takes us through the volume. And we will be doing this in our lab section. So hopefully you have time to become familiar with this in advance, and if not, we'll just look at it in our lab, and this will support your post-lab. All right, determining volume. The volume can be measured directly with glassware, which you may have seen. The graduated cylinder is a great way to measure volumes in a precise way. Pipettes are even more precise. The volume can be measured directly using calibrated glassware, which you may have seen, such as the graduated cylinder. We can also measure the volume of a regular shape by measuring and calculating. And if we have an irregular shaped object, such as jewelry might be one example if you have a pendant, you can use volume by displacement. So we'll go over that as well. If you have a rectangular solid, the volume is calculated as length times width times height. So let's calculate the volume of a gold bar that is, there's my equals, and there are our 3 dimensions. So volume, this will be how many centimeters cubed. And that is 5.25 centimeters, 3.50 centimeters, and 2.75 centimeters. So when we multiply these numbers, we'll have the units just pile up. And I get 50.53 centimeters cubed. I'm going to underline that 3rd digit as the last significant digit. And if I need to calculate a density with this, I'll keep that 0.53. But if I'm just presenting my answer, I will give a rounded answer of 50.5 centimeters cubed. In this one, we are looking for the thickness. So there's a number of ways you can do this. You could say this is my volume and it equals this times your thickness. Or you could rearrange for that thickness and you could say how many centimeters thick will be determined by that volume over those other 2 dimensions. So I'll plug in the numbers, 35.5, divide by 7.5, divide again 3.5, and press equals. So 3 significant figures, and then I would expect that thickness to be 1.35 centimeters. When we look at volume by displacement, we will fill a graduated cylinder partway with water. Now that exact initial volume doesn't matter. What matters is that we record it correctly. So it doesn't have to be 50.0, but we do have to have a measurement that reflects the accuracy of the glassware. So that will be going to 1/10 of the smallest marking. So we take our initial value, and this one I will go ahead and label this as water only. Then we place our sample, our irregular sample, in there. We'll make sure that it doesn't have air bubbles stuck on there. Maybe we'll swirl it around a little bit and get those dislodged. And then we get our final volume. And that is going to be the water plus the jade sample. So if I want to find the volume of the jade, how will I do that? Well, let's just write it out here. 60.5 milliliters of jade together with the water, and I'm going to subtract off my volume of water. So that leaves me with 10.5 milliliters that is just the jade, right? We subtracted off that water. So that's how we can find the volume by displacement for an object that isn't easy to measure. Now, a lot of times we will use the volume to determine the density. The density is like the concentration of mass. It's the mass over the volume. And that is usually reported in units of grams per centimeter cubed for solids, or grams per milliliter cubed for liquids. And if you remember from volume, 1 centimeter cubed is how many milliliters? Yeah, you can just convert between those. The values are equal. So when we think of the density, we're thinking about how concentrated is that mass. The heavier the object per volume. No, I don't like that description. I'll let you read it. All right, we can arrange things in terms of their density. Things that have a higher density will sink. So let's take a look at these different materials. We have ice, we have iron, and we have rubber. Those are our solids. And we have water and honey and hexane. So we put these together and look at where they settle out. We can rank them on the basis of their density. So we know that the water has a density of 1.00 grams per milliliter. So what's the liquid that floats on water? That will be the hexane with the smaller density. And that means that the honey with a higher density will be down below. So let's look for a solid that has a density in between 0.65 and 1.0. And that should be the solid that floats at that boundary. So that should be ice with a density of 0.917 grams per centimeters cubed. Now for solid 2, we're looking for a density between 1.00 and 1.50. So that must be the rubber cube. Finally, we'll look at the one that sinks. It has the highest density here, and that will be the iron cube with 7.87 density. Now, when we do calculations, we can use the density as a unit factor as well. So here's our density of ice, and we've written it with a clear numerator and a clear denominator. Remember, you can always put a 1 on the denominator if there's no number, and when we write it in the second form, we could say 1 centimeter cubed must weigh 0.917 grams. I could also add my label here, 1.1 centimeter cubed of ice is the same as 0.917 grams of ice. Notice that the labels are the same. The units are different, but the labels are the same. So let's write a couple unit factors for these. Here's the density of lead. Get some practice with our symbols. 11.3 grams of lead must have a volume of 1 centimeter cubed. Or if you have 1 centimeter cubed of lead, that will be 11.3 grams of lead. We can do the same thing for chloroform. So here's our value. Don't be fooled by that slanty line. We need a clear top and a clear bottom. So 1.48 grams of chloroform will take up 1 milliliter, or 1 milliliter of chloroform is 1.48 grams. And that's true for chloroform. So anytime we're looking for characteristics of chloroform, such as the mass or the volume, we could use that factor just like a unit factor. All right, so let's do that here using dimensional analysis. What is the mass in kilograms of ethanol that has 1.50 liters? So how many kilograms of ethanol, and this is all ethanol, so it's not as insightful to use the labels. How many kilograms would it be if we had 1.50 liters of ethanol? We're going to use this as a factor to make that conversion. Oh, but it has milliliters, so let's go, and grams. Let's go from liters to milliliters, and then we can use our factor here. So I'll fill in those numbers. And 0.789 grams in 1 milliliter of ethanol. And now we have to get rid of grams and go to kilograms. So let's just double check our units. There's the liters, there's the milliliters, there's the grams. I'll finish filling in my numbers. 1 kilogram is 1,000 grams. So that means that 1.5 liters should have a mass of 1.18 kilograms. That is 1.183, and then I just rounded it to the 3 significant figures here. Okay, using density as a conversion factor. All right, here are a couple more problems. So take a minute to get these started, and then hit play if you get stuck. So here we have a silver medal, and we're looking for the density. Density is how many grams of silver in 1 centimeter cubed of silver. So I have 168.5 grams of silver, and now down here I need to put the volume of just the silver to get the density of the silver. So what have we got? We've got a graduated cylinder with 21 milliliters of water, and when in doubt, draw a little picture. And then we place that silver metal in there, and now it's 37. This is 37.0 milliliters of silver plus water. So we need to do that subtraction. And what is that? I'm going to calculate it so I don't make mistakes. 16.0 milliliters. That is a measured zero, so we need it. And that's the volume of the silver by itself. So that's what's going to go in here. And to make that conversion, we can go from milliliters to centimeters cubed. 1 milliliter is 1 centimeter cubed, just to be formal about it. So I have a 168.5 divided by 16.0, and I get 10.53 grams per centimeter cubed, and that is good to 3 significant figures. So 10.5 grams per centimeter cubed. Okay. Now, I don't know how many of you have seen Raiders of the Lost Ark, but at the end there's a scene where he steals a gold statue. It's a 1.5 liter statue, pretty small, and he tries to replace it with sand. So if he has a bag of sand, we need to find out how much does it weigh in order to replace that statue. Now the statue is pure gold. So we're going to use that density of gold, and then here's what we're looking for. How much does it weigh in pounds? So how many pounds is in the 1.5 liters of gold statue? So how can we get rid of that volume? We might want to draw, just as an aside, we might want to write this density as a factor. So we have 19.3 grams of gold in 1 centimeter cubed of gold, and that's a volume right there. So I'm going to go ahead and put it in there. I'm just going to line it up. 19.3 grams of gold, and that's a mass, so that's something that I can convert into pounds. Whoops. Pretty easily. Oh, it keeps jumping around. And that is for 1 centimeter cubed of gold. Well, we know that 1 centimeter cubed is 1 milliliter. And, oh look, we're getting close to liters. 1,000 milliliters in 1 liter. Great, so let's take a look at the units. The liters cancel here. Mils, centimeters. Great, we're in grams. So, next up, we just need to get that conversion from grams to pounds. So let me go back to that table of factor. Oh, here we go. There we go. 454 grams per pound. Oh, I'm at the very end. All right, so here are grams. Grams need to go down here. 454 grams in 1 pound. That cancels my grams, and we've got our answer. 1.5 times 19.3 times 1,000 divided by 454. And I get, oh, let me make that blue, 63.76 pounds. And it's only good to 2 sig figs. So that is about 64 pounds. 64 pounds of sand. It's going to be large. Not an easy task to replace that little statue on the pedestal, and he was not successful. The whole trap was triggered and the castle fell down and he barely made it out. Okay, so there's some practice using dimensional analysis and using density as a conversion factor. Now, our last section is using percentage, and we see percentages come up in many different areas. So let me just break down the meaning of percent. So per means 1 over, and cent means 100, like centimeters. So we've seen that before. When we look at a percentage, we are taking one part out of the total. And so we could think about the percentage of men and women per class, and this just says expressed to 3 sig figs, and this is assuming that nobody's identifying as non-binary in this particular class. I find that seldom true anymore. Let's see, so our total is 45. So for the women, we have 25 out of 45. And that is, times 100. Just to get that percent unit in there. And that is 55.5% women. And we can show that repeating line over the 5. That means that if we have the 20 men and 45 times 100, that would equal 44.4% men. Okay, just as an example. So when we get percentages in a problem, they contain a lot of information, and writing unit factors from that information is really helpful. So if I say that water is 88.8% oxygen by mass, we can write unit factors. Here I've asked for 2, but we could write more than 2 from that because water is H2O. There's only 2 components. So I'm going to start by writing the grams. This is by mass, so we'll do grams per grams. That means we have 88.8 grams of oxygen for every 100, and the sig figs have to match, 100 grams of water. So that is how we will write that percentage as a unit factor. That is true for water. So here notice they have the same unit, grams per grams, but they have a different label. So that's handy to notice. We'll be using that a lot more later. Now, of course, I could flip that. I could also write that 100 grams of water must contain 88.8 grams of oxygen. But I could also think of writing grams of oxygen to grams of hydrogen. So we do have lots of information in there. I will leave that for another time. Let's take a look at pennies though. This is what we're going to be looking at with our density lab. And pennies were changed in 1982. They were 95% copper with a little bit of zinc, And then they changed to use less copper. Oh, I guess I ought to edit that out. So let's write some factors for this information. For these pennies, we could have, we know that if we weighed 100 grams, if we weighed 100, we know for these pennies that if we weighed 100 grams of pennies, of that mass, 95 grams would be copper. And we also know that if we weighed 100 grams of pennies, that of that, 5.0 grams would be zinc. And we could flip any of those. We could say, well, there is 95.0 grams of copper in 100 grams of pennies. Or we could even compare the amount of copper to zinc. I could say, for every 95 grams of copper, there must be 5 grams of zinc. So a lot of information we could get from those percentages. Let's take a look in terms of an antacid. We'll be working with those in the lab a little later too. So let's say this particular antacid has pain relief with it. It's 10% aspirin by mass. So the question is asking what mass of aspirin, so how many grams of aspirin are in a 3.50 gram tablet. So there we've restated the question, and we need to find a factor that will make that true, that will do that conversion for us. So we'll need to cancel out grams of tablet, and we're going to go to grams of aspirin, and we see it here. That means we have 10.0 grams of aspirin in a 100 gram tablet. Great, so our units cancel and we get grams of aspirin back. Oh, let me go to color. Don't forget to keep that measured 0. All right, now let's take a look at those pennies again. Calculate the mass of copper. How many grams of copper in one penny that weighs 2.5 grams? So let's start with that 2.505 gram penny. And we want to make that conversion. So we can pick one of those factors from up above. This one looks good. It has pennies on the bottom. And it has copper on the top. All right, so of that, 2.37975 grams must be copper. And that is only good to that percentage. So we have 3 digits, the 9 flips the 7, 2.38 grams of copper in that penny. All right, I believe that's the end, 18 out of 18. We have finished the Chapter 2 worksheets, and great, good job.